Okay, so now let's start the next topic in this module, the Legendre polynomials. So what are the Legendre polynomials? They are solutions of the Legendre differential equation. These equations arise from a variety of different physical considerations. Now when you write down the Laplace's operator in spherical polar coordinates, then you see the appearance of Legendre equation and the associated Legendre equation. For example, you must look at, for instance, the book by Quantum Physics by Robert Resnick or Arthur Beiser, Perspectives of Modern Physics. You will see how these Legendre polynomials and the Legendre differential equation arises in the study of the Schrodinger's equation for the hydrogen atom. The physics part of it, of course, I leave it to you for your own investigation if you're interested. So let's turn to the mathematics of the Legendre equation. So what is the Legendre equation? It is the differential equation 5.3 that you see displayed in the slide. Let's see that. 1 minus x squared y double prime minus 2xy prime plus p into p plus 1y equal to 0. That is the Legendre's differential equation. The coefficient 1 minus x squared does not vanish at the origin, and this differential equation makes sense on the open interval minus 1, 1, and so origin is not a singular point, it's an ordinary point. And so what are the coefficients of the differential equation? You divide by 1 minus x squared, and the middle term is what? Minus 2x upon 1 minus x squared, and the last term is what? P into p plus 1 by 1 minus x squared. The middle term and the last term are both analytic functions on the open interval minus 1, 1. So equation 5.3 admits a power series solution, namely a solution of the form y of x equal to summation n from 0 to infinity a n x to the power n. That is the display 5.4 in the slide. Let us differentiate 5.4. Recall that when you have a power series can be differentiated term by term within the interval of convergence. And so if you differentiate this 5.4 term by term and you multiply by minus 2x, because that's exactly what you see in the differential equation, you want minus 2xy prime. So what is minus 2xy prime? Summation n from 0 to infinity minus 2n a n x to the power n, which is display 5.5 on the slide. In the differential equation you have a x squared y double prime with a negative sign, of course. So let us do an x squared y double prime, differentiate 5.4 twice with respect to x. You're going to get n into n minus 1 a n x to the power n minus 2. But after multiplying by x squared, you're going to get x to the power n again. So x squared y double prime equals summation n into n minus 1 a n x to the power n, n from 0 to infinity. Slide display 5.6. Alright, there is also the term y double prime in the ordinary differential equation. Let's see how to deal with y double prime. So when you differentiate the power series twice, you get y double prime equal to summation n from 0 to infinity n into n minus 1 a n x to the power n minus 2. Now observe that when n equal to 0 and when n equal to 1, the terms vanish. So it is summation n from 2 to infinity n into n minus 1 into a n x to the power n minus 2. Now what do? It is important that the exponent of x should be x to the power n and not x to the power n minus 2. So we need to correct this little problem immediately, and the way you do it is to set n minus 2 equal to capital N. In the last displayed equation, you get y double prime equal to summation capital N from 0 to infinity, because when little n goes from 2 to infinity, capital N goes from 0 to infinity. So you get y double prime equal to summation capital N from 0 to infinity, capital N plus 2, capital N plus 1, a capital N plus 2 x to the power n. But remember that the capital N is a dummy index, so we can replace it back by little n, and so finally we get y double prime equal to summation n from 0 to infinity n plus 2 into n plus 1 a n plus 2 x to the power n, which is displayed 5.7 in the slide. So now you see we have the x squared y double prime, you got the y double prime, you got minus 2xy prime. All of them are sums from 0 to infinity and some coefficient times x to the power n. And the last term, p into p plus 1y, that is simple. That is simply summation n from 0 to infinity a n into p plus 1 x to the power n. So now all four terms have the same summation, little n going from 0 to infinity x to the power n, and so now we just have to combine the coefficients. So let's do that. It's n plus 2 into n plus 1 into a n plus 2 minus n into n minus 1 a n minus 2n a n plus p into p plus 1 a n equal to 0. Now we must combine all the a n terms together and we'll get a nice pattern that you see, and this power series is identically 0. When is the power series identically 0? When every coefficient is 0. And now we must equate all the coefficients of this power series to 0, and what we get is a recurrence relation, namely a relation between a n plus 2 and a n. So this recurrence relation is simply a n plus 2 equal to minus a n into p minus n into p plus 1 plus n divided by n plus 2 into n plus 1. N goes from 0, 1 up to infinity. So this is called the recurrence relation. So if you know a n, you can determine a n plus 2 just by substituting in this recurrence relation. So let us set n equal to 0, 1, 2, 3 in succession, and let us find what do we get. Suppose I put n equal to 0, then what do we get? We get minus a0 into p plus 1 upon 2 factorial. So let's record that. So a2 equal to minus a0 into p plus 1 upon 2 factorial. Put n equal to 1, you get a3. a3 will be minus a1 into p minus 1 into p plus 2 upon 3 factorial. Put n equal to 2. Put n equal to 2 and we get a4 equal to minus a2 into p minus 2 into p plus 3 upon 4 into 3 in the denominator. But a2 has been computed in terms of a0 in the previous step. So substitute that a2 over here and we get a4 in terms of a0. Now if you put n equal to 3, what do you get? You will get a5 equal to minus a3 into p minus 3 into p plus 4 upon 5 into 4 in the denominator. But a3 has been determined in terms of a1. So the formula for a3 in terms of a1 should now be substituted, and finally you will get a5 in terms of a1. So the even ones, a2, a4, a6, etc. can all be written in terms of a0, and a3, a5, a7 can all be written in terms of a1. So what do we get? We get a4 equal to a0 into p minus 2 into p plus 1 into p plus 3 upon 4 factorial. a5 is what? a1 into p minus 1 into p minus 3 into p plus 2 into p plus 4 upon 5 factorial. The law of formation is very clear by looking at these two terms by themselves. So what is the law of formation? For n even, namely a2n, it will be minus 1 to the power n a0 into p minus 2 etc. p minus 2n plus 2, p plus 1 into p plus 3 etc. p plus 2n minus 1. Denominator is simple, 2n factorial straight off. What about the odd ones? a2n plus 1 equal to again minus 1 to the power n, a1 will appear, p minus 1 into p minus 3 etc. p minus 2n plus 1, and then p plus 2 into p plus 4 etc. p plus 2n minus 1 upon 2n plus 1 factorial in the denominator. Okay. So we got these two formulas, and now the general solution is you put in all these things together. All the odd ones will have an A1 in front. So you get A0 into big bracket 1 minus P into P plus 1 upon 2 factorial x squared plus P into P minus 2 into P plus 1 into P plus 3 upon 4 factorial x to the power 4 minus etc. A1 into big bracket x minus P minus 1 into P plus 2 x cube upon 3 factorial plus P minus 1 into P minus 3 into P plus 2 into P plus 4 x to the power 5 upon 5 factorial minus etc. The coefficients A0 and A1 can be assigned any arbitrary values. Remember that is a second order ordinary differential equation, so the general solution will involve two arbitrary constants. These are the two arbitrary constants that you see in the general solution. So suppose I put A0 equal to 1 and A1 equal to 0. What do you get? You get a power series involving only the even powers of x. Do the other way around. Put A0 equal to 0 and put A1 equal to 1. You get a power series involving only odd powers of x. So you got a function which is an even function and another function which is an odd function. Now you have an even function and an odd function. They will be linearly independent because they are not identically 0. Neither of these functions is identically 0. You got an even function and an odd function, and so they are linearly independent. So you got two linearly independent solutions of the Legendre's differential equation, and they form a basis of solutions. Now these are two power series. What is the natural question to ask when you see a power series? What is the radius of convergence? You must be able to compute the radius of convergence of a power series. How do you calculate the radius of convergence of a power series? There are two ways of doing it. One is to apply the ratio test, other is to apply the root test. So when factorials are present, as you see in this case, the ratio test is more convenient to apply. So let us apply the ratio test. So I leave it to you as an exercise to check by applying the ratio test that the radius of convergence is usually going to be 1. I say usually. Why do I say usually? Let us look at a simple situation. Suppose P equal to 3. Suppose P happens to be 3. Then let us look at the display in this slide. Let us look at the coefficient of A1. Got A1 into x minus P minus 1 into P plus 2 x cube upon 3 factorial. Rest of the things all have a P minus 3 factor in them, so they'll all disappear. So the second series, the coefficient of A1 terminates when P is 3. Similarly, when P is 5, it will terminate with the x to the after the x to the power 5 term. If P is 2, what happens? Let us look at the case when P is 2. Look at A0. A0 into 1 minus P into P plus 1 upon 2 factorial x squared plus the rest of the things will be 0 because every one of them will involve a P minus 2. Suppose P is 4, then what will happen? You will have 1 minus P into P plus 1 upon 2 factorial x squared plus P into P minus 2 into P plus 1 into P plus 3 upon 4 factorial x to the power 4. Rest of the things will all have P minus 4 sitting in there and they will all disappear. In short, when P is an even integer, the coefficient of A0 terminates and you get a polynomial solution. If P is an odd integer, the coefficient of A1 terminates and we get a polynomial solution. A polynomial, remember, is a power series with infinite radius of convergence. So there are special cases when the radius of convergence is infinite. However, if P is not an integer, then both these series will have radius of convergence exactly equal to 1, and when P is an integer, exactly one of the two series will terminate and the other series will have radius of convergence 1. And so they have completely clarified what is the radius of convergence of these series. And the special case when P is a polynomial, exactly one of the series terminates and we get a polynomial solution, and these polynomials are called the Legendre polynomials. So now let us look at these Legendre polynomials in detail. So once again, assume that P equal to K is an integer. One of the series described above terminates into a polynomial solution, and this polynomial has degree exactly K. That also we have seen. When P equal to 2, it terminates after the x squared term. When P equal to 3, it terminates after the x cubed term, and so on. So the polynomial has degree exactly K. Now we want to understand whether this polynomial solution is going to be 0 when I plug in x equal to 1. So let us call this terminating series as f of x. We know that f of x is a polynomial. Okay, now show that f of 1 is not equal to 0. Here in this slide, I have suggested that you should try this out. But let me walk you through the proof. Suppose not. Suppose f of 1 happens to be 0. Then let's see what happens. Let us put x equal to 1 in the differential equation. So what is the differential equation again? Let us look at this equation 5.3. We have assumed that we have a solution y of x, which is a polynomial solution, and y of 1 happens to be 0. That's what we are trying to rule out. So proof by contradiction, right? So assume that y of 1 is 0, right? So let us put x equal to 1 here. First term disappears. Second term minus 2 y prime 1. Last term p into p plus 1 y of 1. But we have assumed y of 1 is 0. So what is the conclusion? Y prime of 1 is 0. Now that we have concluded that y prime of 1 is 0, let us differentiate the differential equation 5.3 with respect to x. So if you differentiate 5.3 with respect to x and then put in x equal to 0, what happens to the third term? You get p into p plus 1 y prime. And when I could put x equal to 1, that y prime of 1 is going to become 0. Let us look at the middle term. The middle term, when I differentiate with respect to x, we are going to get two terms. We are going to get minus 2 y prime. But I am going to put x equal to 1 and that's going to become 0. And then the other term is going to be minus 2 x y double prime. So you get minus 2 y double prime term from the middle term. From the first term, what are you going to get? When you differentiate the 1 minus x squared, I am going to get minus 2 y double prime 1. So all in all, I am going to get minus 4 y double prime of 1. There's one more term when you differentiate. It will be 1 minus x squared y triple prime. But that 1 minus x squared is going to kill it. So what are we left with? Minus 4 y double prime 1 equal to 0. So y double prime 1 must be 0. So now we have concluded that if we assume y of 1 is 0, then compulsorily y prime of 1 is 0, y double prime of 1 is 0, and I must keep on differentiating the differential equation 5.3 again and again and again, and at each step I should put x equal to 1, and I will conclude that the fourth derivative of y is 0, the fifth derivative of y is 0, all the derivatives of y vanish when x equal to 1, and y is a polynomial. Remember that the p was a positive integer k and we have a polynomial of degree k. So we have a polynomial of degree k such that all derivatives at x equal to 1 vanish. But a polynomial can be written as a Taylor series. You can write any polynomial as a power series around any point that you want. So write the polynomial as y of x equal to y of 1 plus x minus 1 into y prime of 1 plus x minus 1 whole squared upon 2 factorial into y double prime 1, etc. The Taylor series. The Taylor series is going to terminate because it's a polynomial. But y prime of 1 is 0, y of 1 is 0, y double prime of 1 is 0, and so Taylor series is 0 identically. So y of x is identically 0, and that's a contradiction. So I have completely walked you through this proof that when you have a polynomial solution, that solution is not going to be 0 when you put in x equal to 1. you can take the polynomial solution. Here I call it f of x, and we have seen that f of 1 is not 0, and so I can divide fx by f of 1 and I get a normalized solution. This normalized solution, this special solution, is called the kth Legendre polynomial, and it is customary to denote this by the symbol pk of x. So let us record the properties of pk of x. So the first observation is that pk of x is a polynomial of degree k, as I already explained. Then pk of x obviously satisfies the differential equation. So it satisfies the Legendre equation, 1 minus x squared pk double prime minus 2x pk prime plus k into k plus 1 pk equal to 0. Next property, pk of 1 is 1. That is because I normalized it. And it's also clear that pk of x is an odd function if k is odd, is an even function if k is even. And what is p0 of x? p0 of x is 1. So we have listed a number of useful properties of the Legendre polynomials. Now let us prove that the Legendre polynomials form an orthogonal system on the interval -1, 1. And that is stated as theorem 49 on this slide. So what does the theorem state? If k is not equal to L, here k and L are non-negative integers. So I have taken two distinct non-negative integers k and L, and the Legendre polynomials pkx and plx are orthogonal on the interval -1, 1 in the following sense. Integral -1 to 1 pkx plx dx equal to 0. Let us prove this theorem quickly, because it's going to be extremely important, because this is what we started out with. We started this entire module by asking the question, what is special about the trigonometric functions? Why can't we use other systems of orthogonal functions? And here is an example of an orthogonal family of functions on the interval -1, 1. So let us look at this proof of this orthogonality theorem. So pk satisfies the Legendre equation. So that is display 5.8 in the slide. Similarly, PL satisfies the Legendre differential equation, that is the display 5.9 in this slide. Now let us combine the first two terms in the differential equation and let us write it in a more convenient form called the self-adjoint form. So let us combine the first two terms in the differential equation and write it as d dx of 1 minus x squared pk prime plus k into k plus 1 pk equal to 0, 5.10. And again for PL we get d dx of 1 minus x squared PL prime plus L into L plus 1 PL equal to 0, 5.11. Multiply 5.10 by PL and multiply 5.11 by pk, subtract and integrate over -1, 1 and see what happens.